So this is chapter 69 out of your book that we're going to be covering ignition systems. And so want to make sure that we understand the principles of ignition systems. As you go into other classes in the auto program, you'll cover much more details, but basic functional understanding of ignition systems and how they operate is beneficial, and that way you can have a vocabulary to operate from as you go through some of the other classes. And so the purpose of the ignition system is going to be to generate a spark that ignites our air fuel mixture. And so it has to be a high voltage spark. Ignition systems will operate on the 12 volt DC system that we have in our battery, or our battery system there, but they will convert that 12 volts into thousands of volts to be able to jump an open circuit or at a spark plug. And so our spark plugs have a gap, and that high voltage will jump across that gap, which is what we use to light the air fuel mixture inside our combustion chamber. So some of the functions of our ignition system is to change that battery voltage into a higher voltage, has to create a high voltage arc or spark at that spark plug, and distribute that high voltage to each spark plug in the correct sequence. We refer to that as a firing order, or the order in which the power strokes occur in an engine. And then the timing of that spark is very critical, because we ultimately do light our air fuel mixture on the compression stroke, but it's towards the end of the compression stroke. But if that spark occurs at the wrong time, then it affects performance. And I don't just mean on the wrong stroke, but if we have a spark that occurs too early while the piston is moving up, then those expanding combustion gases start to oppose the piston. We lose power from that. If that piston is allowed to peak over onto the power stroke and the spark occurs too late, then we don't make as much power as we could have off of that power stroke. And so we understand already from what we've covered that we have at 3,000 RPMs 25 power strokes a second, or 25 sparks a second from our ignition system. And so the timing of this and when this occurs, the precision of when that spark occurs is very critical. And so on older systems, that was done mechanically. On your newer or more modern ignition systems, we're tracking position of cam and crank and determining which stroke of the four-stroke cycle we're on and precisely where that piston is at in terms of that four-stroke cycle, so that that spark can be timed very precisely within a degree of crankshaft rotation. The ignition system also is responsible for distributing that spark, and so that's more true of some of your older systems that mechanically directed spark, and we're going to look at some of those as well as your more modern ignition systems. But the older ignition systems would literally distribute the spark with a component called a distributor. And so our newer systems have individual ignition system components called coils. Then each cylinder has its own coil to be able to distribute spark, or ultimately at that point just time the spark at the correct stroke and at the correct piston position to get the most fuel economy, lowest emissions, and best performance out of that vehicle. So every ignition system has at least these basic components. We've got a battery involved that is supplying the initial electricity to operate our ignition coil. We'll have an ignition coil, some sort of a switching device that controls this coil and controls when that coil fires. And then we'll have high voltage cables, spark plug wires, you may hear them called, high tension leads, wires that lead us out to a spark plug. So every ignition system is going to be battery operated. It's going to have a coil, some sort of a control, spark plug wires, and a spark plug. And so from your oldest of old to your most new ignition systems or most modern ignition systems, they all will have at least those basic components. And so one of the things to understand about ignition system is that we've talked about power supplies and power sources, and we said, well, a battery generates electricity chemically and an alternator generates electricity mechanically. This ignition coil also generates electricity on the high voltage side. It makes high voltage, and so it is another power source of high voltage. And so older systems made 8 to 12,000 volts. Your newer systems will make up to 100,000 volts of DC electricity. And so the thing about ignition systems is that 100,000 volts is a lot of volts, but it's voltage more like what you would see out of a taser, that it's very high voltage but very little current. And so it's usually it's not something that's going to kill you unless you have a heart problem or something like that, because it's not enough amps. The rule that I generally espouse for the amount of amperage that will kill you is I always remember 51. So 50 volts at 1 amp is enough to kill you. The ignition system, when you consider what's involved, we're jumping an open circuit. And so if we were to ohm or try to measure the resistance of an open circuit, it measures infinite, right? But the voltage that we generate in the ignition system is high enough that it can jump that gap in a spark plug. Even though the center electrode here to the ground electrode there is an open circuit, to high enough voltage, it can jump that gap. But that consumes a lot of energy, and it is a lot of resistance being an open circuit, and so the amount of amperage then that flows is very low, because if resistance is high, then amperage will be low. So if the resistance goes up, amperage goes down. And so in this case, because we have incredibly high resistance, we have very low amperage. The wires alone on this, not to mention the open circuit at the spark plug, but the wires alone ohm at about 4,000 ohms per foot, which is quite a bit considering that a foot long wire like this has basically almost no resistance, right? 0.1 of an ohm or things like that. But a foot long of an ignition wire is about 4,000 ohms per foot. So all of this high resistance, including the open circuit at the spark plug, really knocks the amperage down to where, although it will hurt you if you got shocked by ignition system, it's not enough to actually kill you. So thousands of volts out of our ignition system, they all have those basic components. With our ignition system, it is divided into two circuits. Not unlike how we would divide our starting system into our control circuit and our motor circuit, our ignition system is divided into a primary circuit and a secondary circuit. Our primary circuit operates on 12 volts or lower voltage, and our primary circuit is what controls the secondary circuit. The secondary circuit is thousands of volts, and it's what we use to ignite the air-fuel mixture and direct that spark at the correct timing so that we light our air-fuel mixture. But we're thousands of volts in the secondary. But the primary controls the secondary. And so if we had a problem with the primary circuit, then we would have no secondary. And so diagnostic process-wise, what I always teach my students is we generally will start at the secondary, because if I have spark at the secondary, then I can assume the primary is working and fine. But if I don't have spark out at the secondary, because the primary controls the secondary, then we have to go back and check our primary circuit. So that is the two circuits that we will discuss further in detail and discover how an ignition system can build these thousands of volts off of only 12 volt systems. So the primary circuit is going to consist of these components. So we've got our battery that's supplying power to our primary circuit through the ignition switch. So I have to say this as well. The ignition switch is involved in the ignition system. And so historically in the automotive industry, the only electronic parts or electrical parts on the car was the ignition system. And so this switch quite literally controlled the ignition system, and it turned the ignition system on so we could start the car, and it turned the ignition system off, which shut the engine off. And so this has been referred to historically as an ignition switch, and yes, it does turn on the ignition system and supply power to the ignition system, but we also understand that on a modern vehicle that's heavily electronic, the ignition switch is not just involved in the ignition system, it's involved in what? Everything on the car. But it is part of our ignition system here. And so we have oftentimes a little ballast resistor inside here. Then we've got our ignition coil, and then we'll have some sort of a switching device that ends up controlling the ground side. And so this is a series circuit, this is a load that has resistance, and this is a load that has resistance. And so what ends up happening is, since this is a series circuit, then this will eat about 2 volts, which then means how many volts is left over for this coil out of the 12. If this one uses 2, then this one would have 10. And so this would operate on 10 volts. This would control the ground path here. And so that's how this little series circuit is designed. Ballast resistor uses up about 2 volts, which leaves 10 left over for the coil. The coil operates on 10 volts because at 10 volts, it does that voltage or electrical pressure doesn't push as many amps through the coil and get it too hot so that it overheats and fails. Now, I told you back at the beginning of the semester that there would come a day that I would explain something to you that until now you would have really had no hope of understanding. My hunch is, and typically the case is while we're in person in class, that while I explain that this is a series circuit and this one has a 2 volt drop that uses 2 volts so that there's 10 left over for that, if I would have explained that scenario to you, series circuit, voltage drop, voltage, all of that, the first day of class, it would have just right over your head, right? So I want you to consider and pat yourself on the back how far you've come already in just one semester. And there's still a lot more to learn in the automotive industry and in the automotive classes here at the college. However, even in just this one semester, I want you to take a moment and reflect on how much knowledge you've already gained and a better understanding of how things actually work. And so I congratulate you on that. I'm sure that you follow this concept and this understanding. So this coil is just power and ground. The power side is here, and then the ground path is controlled by a switching device. And so this switching device can be mechanical, and on the older systems it literally was mechanical, would just connect and disconnect the circuit just like a light switch does on your wall, but it did so mechanically. This, what's represented here, represents an electronic switch that's called a transistor, and that transistor controls the connecting and disconnecting of the path to ground. So that's our primary circuit, and that's an electronic representation of how a computer would control that circuit. And so this is just an electronic switch that's referred to as a transistor. Early ignition systems had mechanical switches called points. So then our secondary circuit, the coil is part of both the primary circuit and the secondary circuit. It has 2 separate windings. It has a primary winding within the coil of wire. So inside every load is just a big loop of wire. And so on the primary and the secondary side, the coil has a primary winding inside it that is part of our primary circuit, and has a secondary winding inside it that's part of the secondary circuit. So on the secondary circuit, this is where we collect and produce this high voltage for this ignition coil. The path out to ground, since this is generating the high voltage, voltage will leave here and come into a distributor. And a distributor looks like that, or looks like this in real life. So this would be a distributor, and this is mechanically stabbed into the camshaft. So there's a gear at the bottom of this that would stab on and time with the camshaft. And so as the cam rotates, it rotates this distributor. And so as that distributor rotates mechanically with the cam, so here's one with the distributor cap off of it. So as we turn this gear, you can see that the rotor inside would rotate, and that's what this is referred to as just a rotor, and it rotates as the cam would turn this distributor, and then that ultimately directs spark. So as that coil produces that high energy and high voltage, then that high voltage would come into the center and make contact with this button here, and whichever tower that rotor is pointing at is where that high voltage would continue on to and ultimately out to the spark plug. And so the high voltage, if it gets directed to this tower, then if that rotor is pointing at that tower, then we would have a wire connected out that would go to the spark plug just like that shows. And that high voltage would come out to the spark plug, jump the gap of the spark plug so that it could get to ground and then return back to the battery. So that is your secondary or high voltage system. This is usually where, when we say that we're doing a tune-up on cars, your secondary system here is usually your tune-up parts. So this is where, when we say we're doing a tune-up, we change the spark plugs, the spark plug wires, the distributor cap, and the rotor on the inside. And those would be your typical tune-up parts on your ignition system that we would service for maintenance. So I want to talk a little bit more about ignition coils. So an ignition coil like that, there can be a variety of different shapes, but their construction is all the same. That will have a set of secondary wires that is real fine gauge wire that is thousands of turns. You have some primary windings in the coil, which is thicker, coarser grade wire, bigger wire gauge size that is hundreds of turns. And then in the middle is a soft iron core. And so when we energize that primary circuit, we've already mentioned that when electricity flows in a circuit, it builds a magnetic field. So when that magnetic field is built up, or when current's flowing, we build up this magnetic field. And then we've also established from talking about alternators that when a magnetic field cuts across the conductor, it produces voltage or electrical pressure in that conductor. And so that's why these are in proximity to each other, is as we energize that primary circuit, it builds a magnetic field. This iron core helps to concentrate that magnetic field. And so the ignition coil is, as an electronic device, is a type of transformer. And so you've seen these out in the world before if you paid attention and you're just looking at the top of the power poles. You've seen devices that look like this just out around as you've driven around and lived life. And so what's at the power poles is referred to as a transformer. It kind of looks like a 5-gallon bucket that has some wires coming off of it. And we use that same device in the automotive industry, but we would refer to it as an ignition coil. But ignition coil is a style of transformer, and what we use is called a step-up transformer. What is on the power poles is a step-down transformer, that the power lines are carrying thousands of volts, and they step it down to household voltage, which is your 110 and so forth. What we do in automotive is we take 12 volts and step it up to thousands of volts. So this is some of just another drawing kind of showing that we've got primary windings wrapped around there, and their secondary has many more turns. This is the electrical symbol for an ignition coil. And so they're showing that we've got primary windings on one side, that's our soft iron core, and then we've got secondary windings on the other side. That's often how they would represent an ignition coil in a wiring schematic. So the schematic kind of speaks to, or semi relates, or is similar to the physical construction of the ignition coil. So want to talk about a little more in detail about how this coil builds up a magnetic field and how it produces the high voltage in the secondary. And so we have to have add a little bit more terminology to what we already know that's referred to as dwell. And so dwell is referred to as coil on time. It's the time that this coil has power and ground. And so when that switching device closes, then we get power from our battery that comes in and runs through the windings of our primary circuit and goes to ground, and that builds this magnetic field. So once we build up the magnetic field, then when they open that switching device, the magnetic field collapses, and it'll collapse towards that iron core, and that concentrates that magnetic field. And as it does so, we built the magnetic field in the primary, but the flux lines, or those magnetic field lines, they cut across the thousands of turns of windings in the secondary. And when it collapses, then as that magnetic field collapses, when our switching device opens, it produces high voltage in the wires that it cuts across, or produces electricity. And the reason why it produces high voltage is because there's thousands of turns of windings in the secondary. So it has a lot more opportunity to collect electricity as that magnetic field cuts across those windings. And so if we built the magnetic field off of hundreds of turns, but when it collapses across thousands of turns, then that multiplies the voltage. And so we can take 12 volts then and multiply it to thousands of volts, because the turn ratio between the primary circuit and the secondary circuit becomes a multiplier. If there's thousands more turns of wire in the secondary, then it can take 12 volts times 1,000. That becomes 12,000 volts. All right. And so that's how we end up with high voltage in the secondary. One of the other things that I want to point out to you is that, aside from the science of how this coil works, this is referred to as mutual induction, is that science. But I also want to point out to you that when this spark plug fires, this circuit works opposite of every other circuit that we have talked about up to this point in our auto class. If I wanted to turn a bulb on, I would connect the circuit, right? If I wanted to turn this fan on, I would connect the circuit. But if I want to fire the spark plug, I disconnect the circuit. So this works opposite of all the other circuits that we've talked about thus far. And the reason for that is because when this circuit is closed, we build the magnetic field. But when the circuit opens is when that magnetic field collapses, which is what collects that high voltage on our secondary. That high voltage in the secondary wants to have a place to go to ground. The only place it has to go to ground is to jump that open circuit in the spark plug. Thousands of volts can do so. And so even though that is an open circuit, it will see that as a path to ground. So electricity is a natural phenomenon, right? If we build up ions of extra electrons over here and it has a place to balance out and return back to normal over here, then those electrons will try to balance out in nature. And so in this case, that high voltage will see that open circuit as a path to ground. Electricity wants to move from power to ground. And so it will jump that spark plug gap over there to get to ground. So reiterating, in our ignition coil, it will fire the spark plug when the primary circuit opens. All right? Because opening the primary circuit is what causes that magnetic field to collapse and what generates the high voltage in the secondary, which then has a path to ground through the secondary wires and through the spark plug to jump, which we time correctly so that we light the air fuel mixture at the proper time to make power out of this. And so I'm going to set up a demo for this coil and want to show you how an ignition coil operates in real life. So the components that I have in front of me here on the bench is we've just got a 12 volt battery. We've got our ignition coil and a secondary wire or spark plug wire there with our spark plug out at the end of it. And then we're going to operate this coil on the bench top. This is a distributor that has a set of points. And so this is a condenser. And then these are the points that just connect and disconnect the circuit. So this is our switching device there. The rotor on these will come off. And so this is the points there. Points by themselves would look like this. So you can see on here that these points are just a switch that can open and close. And what causes these points to open and close is this little cam block inside there. This is a hex shape. And so this would have 6 points on this. So the 6 points would open and close our switching device 6 times, which would then be able to fire 6 different cylinders. And so as this rotates, then this little rubbing block on this cam contacts the rubbing block, or the cam on this distributor contacts this rubbing block on our points, and then just opens and closes these points as this distributor would rotate. Simultaneously, when the rotor is on there, every time that it opens and closes the points, we would have a coil wire that would come over to a distributor cap here. And so that coil wire coming over to our distributor cap would come in and send that high voltage into the distributor cap there. Then the center button on that distributor cap would make contact with the button on this rotor right there. And then we have individual towers to all 6 spark plug wires that would go to the 6 cylinders on this vehicle and direct that high voltage to the proper cylinder. And so these older systems had a lot of mechanical ingenuity that they had to be put together correctly to have a car that would run properly. So it started by stabbing the distributor in the proper indexing to this cam. So we had to first off stab the distributor correctly and get it in time with the cam, so that starting out we would have this rotor that would be pointed towards number 1 cylinder on the distributor cap. So if this was number 1 cylinder over here, then we would make sure that we had this distributor timed to where when this was installed, we would have number 1, the distributor cap and rotor would be indexed to where that rotor was pointing towards number 1 cylinder on the distributor cap. And so once this was stabbed in correctly, we're not done with the proper installation, because now you have to route the wires in the correct sequence, which we refer to as a firing order. So a firing order that is common for a 6-cylinder would be 1, 6, 5, 4, 3, 2. 1, 6. So we would make sure that the tower for this the wires for this distributor were routed to number 1 cylinder, then number 6, then number 5, 4, 3, 2. If that distributor were to rotate clockwise. If it rotated counterclockwise, then it had to be mechanically installed correctly for the direction of rotation of the distributor, as well as the firing order on that vehicle, or the order in which the power strokes occurred. So mechanically install the distributor correctly, route the wires correctly to the cylinders that they go to, and in the proper order of that the power strokes would occur. So to set up and bench test this coil, or to set it up so that it would work on a bench top when it's not installed in a car, there's a few things that would be on the car already that I'm going to have to set up for on the bench. So this spark plug would be threaded into the cylinder head, and so it would have a ground because it would be threaded into the cylinder head. And so I'm going to give it a ground this way. This distributor would also be installed to where it would make contact with the intake manifold and the cylinder head and the cam. And so I'm going to have to give that a ground as well and give it a path back to ground, because the circuit is going to want to get back to this battery. And so in order to do so, I have to give them a path back so that current will flow. Now, the next thing is this would all be on the car already. And so if you were hot wiring this and bypassing it like this, then quite literally all that I need to do is to get power over to my ignition coil. And if I get power to my ignition coil, then that ignition system is live. And so with power over to this ignition coil, now when I rotate the distributor, it's generating a spark. I don't know how well you can see that spark, but it is generating a spark out there at that spark plug. And so the other thing that I want to make sure that you do understand is that this is generating a spark every time the points open. So if I manually open the points, it generates a spark. The other thing that I want you to see is that that part doesn't make a difference here. But I also told you that there's a magnetic field there, right? And so if I move this inductive meter toward the bottom of the coil and towards the top, you can see the polarity of that magnetic field change. And so this is no different than if I were to excite this little meter with a regular magnet. And so if I move the polarity of the magnet one end or the other, then it will swing that needle just by changing the magnetic field with a regular magnet. And so this reacts the same way on this coil as it indicates the magnetic field. So we can see that once we built a magnetic field there, and if I hook up my ground back for my spark plug here. But once we build this magnetic field, then if I open the points or open my switching device, the magnetic field collapses, and that's when the spark plug fires. So build my magnetic field, open my switching device, magnetic field collapses, and the spark plug fires instantaneously. And so that's what's taking place with this ignition system. Is we build this magnetic field. When we open our switching device, the magnetic field collapses and we get secondary. So now I want to show a little bit of the different ignition system designs and the generations of these ignition systems. So we started out with distributor ignition systems like this, and so distributors were hung on to for quite some time in the automotive industry. There were still cars that had and vehicles that had distributors in them up to 2010. And so this is our earliest style of technology, or what's considered to be conventional historically for the automotive industry. And so our conventional ignition system in the automotive industry has been distributor ignition systems. With a distributor ignition system, then you would have the distributor, you would have one coil for the whole engine, and then they would have a distributor cap like this that had spark plug wires that ran out to every single cylinder on that motor. And so there was a lot of components to wear out, a multiple amount of components, and one coil had to generate spark for every cylinder on the vehicle. And so when you consider that it takes time to build a magnetic field, and it takes time to fire it. So it takes about 3 milliseconds of time for the magnetic field to build, for example. And for a firing event to occur. Now, if it takes about 3 milliseconds of time, all right? And so we're firing cylinders 25 times a second at 3,000 RPMs. Now understand, that one coil is building spark for every single cylinder on the vehicle, right? And we want to make sure that we build up a full magnetic field so that we can generate a nice hot spark for these cylinders, so that we can light that air-fuel mixture effectively, get it to burn well, and then we have good fuel economy, low emissions, good performance, right? If we only have one coil, now that means for that one coil, it has to fire every cylinder 25 times in our 4-stroke, or 25 times in our 4-stroke cycle at 3,000 RPM. So for a 4-cylinder, that means this coil has to generate 100 sparks per second, right? Well, if it takes it 3 milliseconds to build this magnetic field for a combustion to occur, then in that 3 milliseconds of time, all right, that's 100 sparks a second times 3, all right? That's 300 milliseconds, right? But that's a 4-cylinder. If we double the cylinders for one coil for a V8, all right, that's not 300 milliseconds, that's now 600 milliseconds. Except 3,000 RPMs is not the max RPM for these engines, right? A lot of engines will redline at about 6,000 RPM. Well, if we double those numbers because we're doubling the RPM, then now we're at 1,200 milliseconds. So some of you math whizzes have discovered the problem, right? There's only 1,000 milliseconds in a second, right? So what happens is at high RPMs, when I have one coil for all the cylinders on a V8, I start to run out of time to fully saturate this coil with a strong magnetic field to be able to ensure that I get a nice hot spark. And so on our distributor systems, the performance starts to suffer at higher RPMs, fuel economy goes down, emissions go up, and so this became an inferior system to modern systems. Now, a lot of components involved. Early systems were completely mechanical. They had points just like what I demoed for you on the benchtop. That moved to electronic ignition systems that were still distributor. This is an electronic ignition system here. This is also an electronic ignition system here that has a little module as a switching device. It's got a sensor inside there and a module as a switching device, computerized. The sensor looks like this if you took it out. So these are simple sensors that just tell this module, fire the coil, fire the coil, fire the coil. The module is what controls the primary circuit being grounded, and when we open the primary circuit, it fires. And so these modules were very simple, and as you can imagine, this one's the old one, and that one's the new one. As time went on, these modules, older computers like this one from the 80s, the computers were big back then, and as time went on, then they got smaller and smaller and more sophisticated. So that's our conventional ignition systems. Still a lot of mechanical parts, and then there was a lot of parts involved. That on this system, if we described our ignition system, we would say not only did we have our primary circuit components where we had our coil and we had a switching device and some sort of a trigger, right? Which is a sensor. But on the secondary side, we had the distributor cap and rotor. We had spark plug wires for every cylinder. We had a coil wire and we had spark plugs for every cylinder. So a lot of complexity. One coil required a lot out of that one coil to be able to produce spark for every single cylinder. So because the high RPM and producing a hot spark at high RPM was the primary concern, that led to what we would call waste spark systems. Waste spark systems have multiple coils. And so these multiple coils, this one is 3 separate coils right there, 1, 2, 3. And then what they did with this is for a 6-cylinder engine. So this system has less complexity. They got rid of the distributor, hence it's called a distributorless design. So this is a style of distributorless ignition system where they got rid of the distributor, and in getting rid of the distributor, they reduce the complexity of this system. If there's less parts involved, then there's less parts to fail, which then makes the system more reliable. They solved another problem by adding multiple coils so that now this coil only has to supply spark for 2 cylinders, and 2 cylinders for this one and 2 cylinders for this one. And so by adding more coils to the system, they ensured that we could always produce a nice hot spark, which gets us better fuel economy, lower emissions, better performance. So the problem with this system, which led to the next system, is that I don't have individual control over the cylinders. If I wanted to change the spark timing or when that spark occurred to this cylinder, since it shared it with this coil, then I had to change it for that cylinder too. And the same is true of this coil and this coil that they supplied spark for. And so I did not have individual control over these components. So if I needed to change spark timing for this one, I had to change it for this one. And the way that these systems work, by the way, you're like, how can it fire 2 cylinders at the same time? So if you remember when we talked about engines, we talked about companion cylinders. So companion cylinders is the idea that we have pistons that make the same movement, but they're on different strokes, right? So on any of these even numbered cylinder motors, they would have companion cylinders. And so the companion cylinders the piston makes the same movement, but they're on different strokes. So as the 2 pistons are coming down, this one may be on an intake stroke, but this one will be on a power stroke. And as they come up, then this one would be on compression, this one would be on exhaust, right? And then when they come back down, this one would now be on an intake stroke, and then this one would be on a power stroke, and then this would be on exhaust, and this one would be on compression, right? So on a waste spark system like this coil will fire every revolution of the crankshaft. And so it'll fire both cylinders. And so we've already said that we fire the spark plug. We want to light the air-fuel mixture towards the end of the compression stroke. So if the pistons are moving up and this one's on a compression stroke and it gets fired, this one would get fired too at the same time. But if this one is coming up on a compression stroke, this would be coming up on a exhaust. And so in this case, they would fire and use this spark on the compression stroke, but then this one would be wasted since it fired on the exhaust stroke, hence the name a waste spark system. So one spark is used, it does fire these both at the same time, but one spark is used and one spark is wasted, and it would alternate, right? That this time it would use this one, waste this one, and then the next rotation, use this one, waste this one. So waste spark systems there. So then, because we don't have individual controls, that any adjustments to this system electronically had affected two cylinders at the same time, that led us to the more modern ignition system, which is coil on plug. So coil on plug, what we have got rid of here is now we've got rid of spark plug wires pretty much, right? I don't have dedicated wires, and what we have is a coil and a spark plug. Now, technically, to be consistent with what I talked to you about earlier, I said all ignition systems will have a coil, they'll have some sort of switching device, they have wires, and they have a spark plug, right? So if we look at these coils, this is still considered the spark plug wire. It's a boot on the coil that plugs in, right? So they do technically have a wire, it's just a very small wire, right? Spark plug goes right into the end of this. There's our coil portion there. This is our switching device. The module is now built into each coil in this case. And then we've got our coil, switching device, wire, spark plug. So still consistent. But and in some cases, the switching device, this one only has a couple of wires. You can see the little heat sink on this one, and then the amount of wires tell us that the module or the switching device is built into this coil. With this one, it only has a couple of wires, which would be power and ground. So if it only has a couple of wires, then this module or computer that controls this coil is someplace else, all right? But careless to what, when we move to coil on plug, the big advantage, we have plenty of time to build a magnetic field. The simplicity of this is very, very simple. It's less complex. A coil on a spark plug, right? And then, so that makes this system incredibly reliable, all right? And so reliability, performance, emissions, fuel economy increases with this technology. And then in reality, the systems do become more reliable because they become less complex. The earlier conventional systems, distributor systems, had a lot of components involved, and that's just more parts to break. The waste spark systems or distributorless coil pack style of systems, they had less complexity than the conventional, but they still had a lot of parts involved. Multiple coils, spark plug wires, spark plugs, right? Then we get to this, okay, fine, we have multiple coils, but no more spark plug wires, just a coil and a spark plug. So you can see the complexity of the system actually, with time, got less complex from a component standpoint than it did in earlier systems. And so it's not always true that as the technology increases that things become more and more complicated. Electronically, yes, this is more complicated and sophisticated. But as far as the amount of components to deal with, diagnostic process for diagnosing these, way simpler. Most of the time to diagnose ignition system misfires on a system like this, if this coil, I suspect that it's misfiring because on this 4-cylinder I have 4 identical coils, I just move this one to the spark plug hole where this one was, right? If I just move these coils and switch spots, if the misfire follows the coil, then I know my coil is causing my misfire. So the diagnosis can be pretty simple on some of your newer stuff.